morning, everyone. Today we are going to have a lecture on Introduction to Path Planning. What is path planning? Path planning involves determining a feasible route from a start to a goal while avoiding obstacles, crucial for autonomous systems. And it is essential for autonomous systems to operate independently without the help of a human. And path planning ensures safe navigation in complex environments while minimizing time, distance, and energy consumption. Path planning is fundamental for robotic systems to perform tasks in structured and unstructured environments, whether on land, air, sea, or space. Coming to the applications of path planning, it is applicable for route planning for self driving cars, considering traffic, obstacles, and road conditions, which are highly dynamic in nature. Flight path optimization in 3D space for tasks like delivery, surveillance, and mapping. Then, efficient movement of robotic arms in manufacturing, minimizing collisions and optimizing cycle time. The figure here shows the workspace in recent robotic path planning competitions, where the obstacles and the target locations are highly dynamic. Evolution in path planning methods. First, in the year 1956, Etzger Dijkstra introduced the shortest path planning algorithm, which laid the foundation for later developments. Next, in the year 1968, Peter Hart, Nils Nilsson, Bertram Raphael combined Dijkstra's algorithm with heuristics for improved efficiency. Then in the year 1985, Lydia and Jean Claude enabled path planning algorithm in high dimensional spaces using sampling based methods. Then in the year 1990s, Stephen M. Lavelle facilitated real-time path planning in complex environments. Next, in the year 2008, Sertak and Emilio ensured optimal paths in asymptotic conditions with rapidly exploring random tree (RRT) refinement. In the year 2013, Sergey Levine used deep reinforcement learning for complex navigation tasks. Now, let us see the types of path planning. First one is single agent path planning, and it involves finding a path for a single autonomous agent from a start to a goal location while avoiding obstacles. Example is determining a route for a mobile robotic system in a warehouse, and the challenges involved here are in handling dynamic obstacles or navigating through complex or high dimensional spaces. Next, we have multi-agent path planning, and this multi-agent path planning addresses path planning tasks for multiple agents that must coordinate their movements to avoid collisions and reach their goals. An example here is in coordinating multiple drones for simultaneous delivery tasks, and the challenges involved are in avoiding obstacles or avoiding the collisions between the agents and ensuring efficient coordination and communication between or among agents. Next, we have static path planning. Static path planning focuses on path planning in environments where obstacles and goals do not change over time. Example, solving a maze with fixed walls and goal locations. Solving a path for a mobile robot to reach a fixed target while avoiding obstacles, where the target is fixed, static in nature, and the obstacle locations are also static in nature. The challenges in this case of static path planning is in optimizing the chosen path, whether the chosen path obtained through the static path planning approach is optimal or not. There is the biggest challenge. Next, we have the dynamic path planning. It involves planning paths in environments where both the obstacles as well as the target locations can change over time. And the severity is in multiple obstacles which are dynamic in nature and multiple targets which are also dynamic in nature. Example, navigating a car through traffic where other vehicles and pedestrians move unpredictably. And the challenges lie in adapting to real-time challenge changes and uncertainties and replanning and adjusting paths on the fly. There is another example in dynamic path planning is in robotic smart needle interventions, which is towards minimal invasive surgical application. Here we have the initial point where the needle can enter, and there is a target location, and this is basically inside the human body. And now the flexible bevel tip needle, where the theta is bevel angle, could be 30° or 45° in certain applications. So this flexible needle can enter through the entry point, which is the initial point, and by avoiding the obstacles can be steered to reach the target. And this path is a path which is formed in order to avoid the dynamically moving obstacles as well as the target region, because this environment is inside the human body and it is made up of tissues and fluids and blood vessels and bones. So there is a highest chance of having these obstacles changing and also the target changing over time. So as you can see here in this simulation, this is how it is. The needle enters here and the obstacles keep changing dynamically over time, and the needle tip is moving towards the path found optimally without colliding with the dynamic obstacles and reaches the target. In the real time, the target also will have the change in location due to the interactive forces that happens due to the interaction with the needle inserting in the tissue domain. As you can see that by avoiding the dynamic obstacles, the needle is inserted to reach the target. Here we have static target, but it is in real time. The target also may vary because of the dynamic tissue movement. And now let us revisit the search algorithms that we have seen in the previous class quickly. We have studied three types of forward search algorithms: breadth first search method, depth first search method, and A-star search method, where first in first out, last in first out are the approaches or strategies used in these two first techniques, and A-star outperformed these two techniques that we have seen. Now sophisticating the priority function f of x makes a general search problem into a path planning problem, because priority function how we design that is the key strategy in these three search algorithms. Now, by sophisticating this priority function f of x will make a general search problem into a path planning problem. And the A star among these three approaches has the most sophisticated and optimal priority function. Now, let us see about A star search. A star search is not just interested in finding paths, but also the optimal path. The star is meant for indicating optimal path or the optimal solution obtained from this algorithm. For that, we use heuristic function h of x along with the cost function g of x. So, the next point is given by f of x plus h of x case. The new state can be obtained by the inclusion of f of x and h of x, or you can see that precisely it is the heuristic function and the cost function f of x. Let us say this is f of x or g of x being the cost function. Both considering the cost as well as the heuristic, the next state is obtained in the A star approach. In most of the cases, h of x is the Manhattan distance from the current location to the goal location, or by expression it is given by h of x equal to modulus of the distance between x coordinate of the goal location and the actual or current location of the x coordinate plus y coordinate of the goal location minus y coordinate of the current location's magnitude. Now, let us talk about the greedy search in path planning. A search algorithm that selects the most promising node based on a heuristic evaluation to reach the goal as quickly as possible. The greedy search in such a way that from the initial point you reach to a node, let us say. From that you try to reach the goal as quickly as possible based on a heuristic evaluation, and this is called greedy search approach. And here we are minimizing the cost or estimated cost from the current state to the goal using a heuristic function h of x. And this approach, unlike the A star approach, here we have f of x equal to h of x always. The example here is, let us say we have to find the shortest path on a 2D grid from the location 0, 0 to the goal location 5, 5. This is 0, 0 location, 5, 5 location is the goal location. Initially h equal to 10 here, and for 1, 1 h is becoming 8. Heuristic function takes the value 8, which is the least possible value. Accordingly, it reaches here where h becomes 6, and here it reaches where the heuristic function takes the value h equal to 4, then 2 accordingly. Similarly, it will go to 2, 2 after that and so on. That is the way it reaches. Precisely, it would look something like in this figure. It started from the initial location and step by step it reaches the goal location, which indicates that it is not only finding a path which is the general approach to reach the target, but also it makes sure that the path is the optimal path. The algorithm here has the structure of a general search algorithm, where the path obtained is the optimal path to reach the target location. Now, let us have the comparison between greedy search approach and the A star search approach in the perspective of path planning. A star is generally more reliable for finding the optimal path than greedy search approach, given an admissible heuristic. Greedy search can be faster in some cases because it only considers the heuristic and does not keep track of the path cast. However, this comes at the cost of potentially missing the optimal path. Both the algorithms, greedy as well as the A star approaches, rely on heuristics, but the A star approach uses a more comprehensive evaluation function, making it less dependent on the heuristic alone. Now, let us see the potential fields method, the introduction to this approach. It uses artificial potential fields to guide the robots from start location to the goal location, where, as you can see from the schematic, this is the work volume of the robotic system, and the robot is somewhere in the target location, and it has to reach the somewhere in the initial location, and it has to reach the target location, and the obstacles are given higher potential field. So, the robot will have the path avoiding the higher potential field area, thereby it is having the path formed in between the obstacles to reach the target location. Precisely, the potential fields method uses artificial potential fields to guide the robotic systems to maneuver over the path to reach the target. Here, attractive force is generated towards the goal and repulsive force is generated to be away from the obstacles. Near the obstacles, once the robot is moving, it will have the repulsive force from the obstacles, so that the robotic system avoids the collision with the obstacles. And towards the goal, the robot finds an attractive force to reach the target. The attractive fields pull robotic systems toward the goal, whereas the repulsive fields pushes the robot away from the obstacles. So, we model here the attractive and repulsive potential fields as follows, which are the key attributes for this algorithm. So, the attractive potential field is given by UATT, U suffix ATT, which is equal to half KATT into the norm of x minus x goal square, and the repulsive potential field U suffix rep is given by half into k rep multiplied by 1 upon x minus x obstacle norm minus 1 by d naught whole square. Here x is the current location and x goal is the goal location, and k at ATT and k repulsive k REP are the gain factors used in attractive potential field computation and repulsive potential field computations respectively, and d naught is the distance at which the repulsive force or repulsive potential starts to take effect. Therefore, the net potential field here is given by U total of the input x equal to attractive potential field plus repulsive potential field U ATT plus U rep. Now, we can calculate the lines of forces which will be the paths from the initial location to the goal location for the robotic systems. And these lines are given by the formula f of x equal to minus gradient of u total of x comma y comma z, which is further the derivative of that, which is expressed as minus of dou u total upon dou x with the unit vector x hat plus dou u total upon dou y into the unit vector of y plus dou u total upon dou z into the z unit vector z hat. So, the advantages of this approach are it is simple and it facilitates real time path planning for the robotic systems and other autonomous systems, and it is flexible for dynamic environments where both obstacles and multiple targets are dynamic in nature, which means their locations vary with time. And the disadvantages, we can get stuck in local minima instead of having the global minima. And this approach requires careful tuning of the parameters associated with the update algorithm or the update law. Now, coming to the introduction to sampling techniques. The definition of sampling based path planning is such that sampling techniques involve generating random samples in the environment to explore possible paths. Upon exploration, depending on the consumption of time, we eventually reach the target. The purpose of this sampling based path planning approach is that it is used when the environment is too complex or unknown for exact methods, and it helps in finding feasible paths by randomly exploring the space. Random sampling. Let us talk about random sampling now. The concept of random sampling is that generate random points in the search space and connect them to form a path depending on the current situation to reach the target, considering optimality and avoiding obstacles. The process here is randomly select points within the workspace, check connectivity between points and form a graph. The usage of this approach of sampling or random sampling is that it is useful in simple environments where a complete map is not available. Now, let us have a brief introduction to RRT, which is a rapidly exploring random tree. The concept here is incrementally builds a tree by randomly sampling and expanding nodes. That means we start from the goal and then select a node, connect it and search for node which is closer to that and connect it, and select some other node and see the distance which is closer, connect it. Then select a node and select another node and see whether which is closer, connect it. So, thereby developing the tree to reach the target randomly. The nodes are selected randomly, and by having a metric check, we can connect these nodes together to form a branch of the tree to finally reach the target. The process here is that start from an initial point and grow the tree by randomly sampling the space. connect new nodes to the nearest existing node. The advantages of this RRT approach is that it is efficient in high dimensional spaces and can handle complex and high dimensional environments easily. Now, having seen the brief of RRT, let us talk about RRT star. As the name indicates star, which means that the path found by this approach is optimal in nature. The concept here is an improved version of RRT that optimizes paths by rerouting and connecting nodes. So, we have a target here, we have the initial point here, and these are the obstacle locations. So, the process here is, it is similar to RRT, but focuses on refining paths for optimality. So, here it goes for the random node, and from the first random node it searches the nodes randomly and selects one based on the closeness to this node, and then it continues, and then by having the nearby node selected, they have the radius around that node, and in that radius around that node we have so many random nodes selected, and see whether from this node to this, and from here to here, or from here to here. So, connecting this node to the nearest node will form the path, this and this and this, but this algorithm checks that what is the path here and here, because this path say P2 and this path say P1, the total length of this path is compared and the minimum path is taken by neglecting this. Like that, another random sample point or the node, then around which the same search region is put upon, and then so many nodes are there. From that we choose one node and see whether how it is getting connected to this. Now, the path is here, this way to reach this or this, accordingly the shorter path is chosen. Likewise, this path is continued towards the target or the goal region by having the selected space region around the newly chosen random node. So, the advantages of this approach is that it provides better path quality as compared to the basic RRT, and it balances exploration and optimization. And by this way, it reconnects the nodes to improve path quality. The path that is getting obtained here finally tunes further to provide much optimal path. Now, we see the introduction to probabilistic roadmaps, PRM. As can be seen here in the graph, this approach builds a roadmap by randomly sampling points and connecting them to form a graph, as can be shown in the schematic. The process involved here is sample points and connect them to create a graph. Use graph based search algorithms to find paths from this graph. The advantages of this approach is that it provides better path quality as compared to the basic RRT. Probabilistic roadmaps effectively handles complex high dimensional environments by creating a roadmap through random sampling. Yes, so as a conclusion to this lecture, we have seen the introduction to path planning generally, and then we have seen various path planning approaches involving probabilistic roadmaps, rapidly exploring random tree, and RRT star, A star, greedy search approaches, how a search approach becomes path planning approach by involving heuristic approaches. And we have seen couple of applications briefly towards mobile robot maneuvering to reach a target, and also we have seen a simulation of a robotic needle to reach the target in the drastically changing dynamic environment inside the human body to reach the target. In the next class, we will be seeing an elaborate lecture on RRT, that is rapidly exploring random tree, and probabilistic roadmaps with the application in minimal invasive surgical robots. Thank you so much.